My name's Tim Niven. I'm a PhD student at National Tsinghua University here in Tainan, Taiwan. My background's actually philosophy. I did some graduate studies in philosophy of science and metaethics and a little bit of logic in New Zealand, where I'm from. I became interested in machine learning quite a bit later in life and decided to pursue graduate studies here where I happen to live in Taiwan. Obviously, it's quite a natural extension from philosophy into machine learning to do something like argumentation mining and the associated natural language processing base.
I suspect listeners will have some of the general ideas, but not necessarily be familiar with specific things like the augmented reasoning comprehension task. Could you describe maybe that specific problem or talk generally about that class of problems?
So the argument reasoning comprehension task is concerned with what are called inferential licenses. So for humans, when we hear an argument, for example, the conclusion, you should take an umbrella for the reason it's raining, we know that that forms an argument because we have something that licenses that inference. And for us, it could be, for example, that we know it's bad to get wet. That's kind of a difficult problem for computers because they don't have any of this background knowledge. They don't know that it's bad to get wet. In argumentation mining, if you want to do this kind of reasoning, you need to discover these warrants, and then you also need to reason with them. So the argumentation reasoning comprehension task will put that discovering warrants problem on hold, which is a very significant one, but put that on hold and just focus on reasoning with given an argument, a claim and a reason, and a candidate inferential license or warrant.
I think it's fair to say that's a really high-level task. Is that correct, or do you have a more articulate way of describing it?
That's exactly how I would describe it. It's very high level. So not only do you need to do this reasoning, and it's informal logic, it's not formal logic, so it doesn't really permit of a clean logical distillation. We have informal logic, and we also have a lot of extra world knowledge. So the example in the paper, the claim is Google is not a harmful monopoly. The reason is people can choose not to use Google. And the offered warrant is not all other search engines redirect to Google. So if you just take that example, you need to know how the concept of monopoly relates to web directs in the context of search engines, which is pretty high level.
Do you have a sense of how historically people have approached these types of problems when trying to do them algorithmically?
Actually, the argumentation reasoning comprehension task came out in the era of deep learning's popularity. So as far as I'm aware, an approach other than a deep learning approach hasn't been tried yet. For argumentation mining more generally, previous approaches relied on custom features that were reasonable given the surface features of argumentative text. For example, discourse markers. Take therefore or because. If you look at argumentative text, you'll find that the discourse marker therefore is a very reliable indicator of a relationship between a premise and a claim. So the earlier argument could be, it's raining, therefore you should take an umbrella. That's very clear what the argumentative relations are when we have those kinds of discourse markers. But of course, those discourse markers aren't always present, which raises the question of how far you can really go with just surface features without really understanding the meaning behind the language, and maybe some more pragmatic things about who the people are, what their communication goals are, and so forth. So it's actually a really complicated problem, which is relevant to our discussion about deep learning because it's still a question of just how deep beyond these surface features deep learning is getting. And that's kind of something that our research touches on. It doesn't seem that BERT has gotten very deep beyond very shallow surface statistics.
So when I look at a problem like that, it seems like a symbolic approach would be one that might have a lot of benefits, or maybe something Bayesian, but definitely something that has more of a model to it, in contrast to a lot of the deep learning techniques like BERT, which are very black box, and we don't really have a theoretical basis behind them per se. It seems like there's almost like a clever leap here to think to apply BERT to a problem like this. What led you to that idea?
I think it's when you first start to learn about neural networks, it's hard to really know what they can and what they cannot do, just for the reason you mentioned. So I know some people that would, for example, hold the belief that train BERT on lots and lots of naturally occurring text and it will learn world knowledge. I've heard people make that claim, even make it last week at ACL. I don't hold that view, but I think it's still interesting to try and apply these cutting-edge techniques to problems, even if they seem unlikely to succeed, just to see how they do.
Yeah, I mean, BERT's obviously doing really amazing things in a lot of cases. I guess I'm a little curious, given your comments, is there a sort of a nature-nurture here, or maybe we should call it nativism versus empiricism?
The empiricism versus nativism debate in artificial intelligence is one that should probably get a bit more attention, in my opinion. There is one popular argument due to people like Yann LeCun, which could be described as an argument from engineering success. And hopefully I'm not going to present a straw man of this argument. Since we've been using deep learning, and our approach has been to try and learn as much as possible and to put in as little as possible either prior knowledge or inductive biases. Yann LeCun famously said inductive bias is a necessary evil, although I'm still not convinced of why it's an evil. But it is true that in doing so, we have seen better and better performance on our in-distribution test sets, which is to say the test sets that come from the same distribution as the training set. And even though we don't understand deep learning sufficiently, so the argument goes, these successes are a strong reason to believe that we're going in the right direction, that the right direction is to put as little prior knowledge into our models as possible, to learn as much as possible from the data, or as someone put it to me the other day, if it can be learned, it should be learned. So there's a lot that can be said about this argument, but restricting to our work in conjunction with a lot more and a lot better work, previous work from other researchers on this problem of model solving data sets and latching onto spurious statistics. Insofar as this is happening, it obviously undermines the engineering success argument, because the success isn't the kind of success we really want. We don't want to succeed in exploiting these spurious statistics in our data sets and giving us brittle solutions that won't generalize. So insofar as that's the case, then the argument from engineering success is undermined, at the very least in the sphere of natural language.
Thanks to this week's sponsor, Brilliant.org. Brilliant is a problem-solving website and app with a hands-on approach and over 50 interactive courses. These courses have a storytelling, code writing, most importantly, interactive challenges, and lots of problems to solve. If you're someone who listens to Data Skeptic to learn, and if I'm sometimes over your head, well, sorry about that, but their probability courses and their statistics and fundamental math courses are exactly what you guys will need. They're fun, they're good explainers, and they really make learning enjoyable. There's plenty for more advanced listeners as well, and I find Brilliant to be an excellent way for me to expand my breadth of knowledge. There's only so many hours in the day, I can't learn everything. But when I'm ready to taste my appetite and see how much I want to bite off, I'll head over to brilliant.org/dataskeptic, where listeners can get 20% off a year of Brilliant Premium. Over 8 million people learn on Brilliant, and you can too. Head over to brilliant.org/dataskeptic. Brilliant.org/dataskeptic. And for listeners who don't know, I mean, we've been covering BERT, or as this airs, we are in the midst of covering BERT on a couple of episodes. So we can maybe take for granted that listeners know what it is and some of the background on it. But could you talk about how it was, what it took to adapt it to this particular problem?
Yeah, so our adaptation essentially follows the recipe in Google's original paper. We actually just put a linear classifier at the end of it, and we do fine-tune the whole architecture. I think it's definitely an interesting question whether that linear classifier at the end is the bottleneck. Does BERT have a lot more knowledge in there that we are unable to extract with a simple linear classifier? That's a possibility, I guess, logically.
That's interesting, yeah.
I guess what probability you'd put on that succeeding, I guess that's pretty subjective.
What were your expectations before running the tests and experiments? How did you predict BERT might fare, especially in light of how much positive press it's gotten?
Well, I was quite doubtful of BERT. I don't believe necessarily that by just doing statistical language modeling on text, you can get all the kind of world knowledge and do the kind of structured things with this incredibly complex latent structure of reality that's hiding behind the text. I personally think it's going to take a lot more. So I didn't expect it to do very well.
And how did its performance meet your expectations?
Well, it's quite surprising. I mean, the first thing you need to note is the mean of BERT's runs over 20 random seeds was not as high as the previous winner. That can be down to what's called degenerate runs in the BERT paper. We have a really small data set like this, which is 1,200 data points for training data only. It's tiny. So you do find those degenerate runs where the training accuracy and then, of course, the dev and test set accuracy never really get very high. So we had about 5 of those in our judgment. And if you take those out, then we are pretty much on par with the previous state of the art. But the surprising thing was it had a lot more variance. So at its best, its maximum performance, it was just 3 points below the human baseline. And that's the human untrained in reasoning baseline. So that looked a little bit surprising.
Why is that?
Well, as I said, I didn't expect that BERT should have any of the required world knowledge needed for this task. That was my intuition.
How conclusive do you find that to be then? Does that, it could be sort of BERT is in that state, but for reasons other than what you're hypothesizing. I don't know what those would be, but I guess I'm just curious how conclusive you find that to be as a probing of what BERT is.
It's obviously important not to take your results at face value. And there's a lot of research now. There's quite a growing body of research that is concerned with us solving data sets and not solving tasks. So the idea that your training data and your testing data come from the same distribution can be the fact that there are artifacts in the data set from the collection process, from the annotation process, that provide some statistics that models have shown a tendency to latch onto. And they can increase their test set performance by latching onto these statistics that are not what you want to learn and don't relate to the task, but then they appear to be doing really well. So we wanted to investigate whether this was the case.
I'm curious if you have a sense of what BERT lacks. Is there a brilliant paper that's going to come out in the future that's going to be the next iteration and will jump far ahead in these rankings because of some clever innovation? It seems to me you might think there's a ceiling. I guess I'm curious how close we are to it and what steps might get us closer.
Obviously, as scientists, we have to use our own intuition of what's likely to succeed, where we should invest our time and our effort. And if you ask me, this is a subjective opinion. Unfortunately, I can't back it up with evidence and papers right now. But my feeling is that there is a ceiling with language modeling the way it's done now, with the model architectures. And that I think that the problem is very complex. The latent structure of reality behind the language is a super complex thing. So how would a model learn that, and how would it learn it from text? It does seem to be a little bit of a Chinese room argument to me. I think grounded language learning is a really positive direction. And I also think that taking cognitive science, the results of cognitive science, seriously is also a promising approach. Because if you read, for example, childhood language acquisition literature, the computation problem they're trying to solve is how do children make this problem more tractable? So like Quine's indeterminacy of argument, so many billion potential reference if you really start to enumerate them all, but they map it so reliably to the right reference. So I think if we pay more attention to these things, maybe we'll get some inspiration to find something that can really make progress on these difficult tasks.
One of the aspects we haven't touched on particularly deeply is the adversarial test set. Could you talk a little bit about its role in the experiment and why you added that to the whole process?
After we discovered that there were linguistic artifacts in the data set that were unevenly distributed over the labels, and we designed our experiments to show that models are relying, and BERT and also the BILSTM and bag of vectors, the models are relying on these statistics. It was another nail in the coffin, I guess. If you can eliminate those statistics, how well can you do? It turns out it was random, but there was also another motivation behind that, which was saving the data set. The data set was designed in actually a very clever way so that the alternative candidate inferential license together in conjunction with the reason leads to the negation of the claim. So that gives the basis for pretty much solving this problem with the data set. It now still stands as a good data set and a good problem, a very challenging one, and with a random baseline currently.
Yeah, tell me a little bit more about the data set. From what I understand, it's available online. Could you talk about who the intended audience is and how they can get a hold of it?
Yeah, so at the moment, the so-called adversarial data set, whether or not that's the best name, it's available on our GitHub on IKM Lab. It's associated with the paper. There's a link in the paper. If you go onto the GitHub, you'll find an adversarial dataset folder with all the data. The intended audience is really people who are interested in argumentation and this more high-level reasoning and informal logic.
I'll have a link to that in the show notes so people can check it out. What will they find in that data set?
Yeah, so we've got double the size data set now. We've got 2,400 data points. They cover a range of debate topics. The dev and test sets also cover different topics than the training set to make it extra difficult. So it's a very challenging benchmark for informal reasoning. And if you really want a challenge, I think you should definitely take this one up.
There are proponents of deep learning who will point out that as far as we've been able to do so far, increasing the data set size, the corpus or whatever you want to call it, has benefits to the model, and it doesn't seem to be too strong of diminishing returns. That is to say, there's more to gain by just muscle mass at this point. I'm curious to hear your thoughts on ideas like that from your background in philosophy of science. I don't know how we can conclusively argue either way that, more data will make BERT more impressive and suddenly it'll be magically AGI versus, there's something missing in it that makes it different from us in some fundamental way.
Well, first, let me say that I'm a bit skeptical. I mean, by all means, if people pursue this line of research and succeed, then I'll be the first one to happily congratulate them. I am skeptical because we haven't really demonstrated some of the things that we really expect from our best models. We haven't just demonstrated compositional learning. We haven't demonstrated systematic learning. Our models continue to be brittle, to be easily attacked with adversaries. And we also have this problem, which our paper highlights, the problem of solving data sets and not solving tasks, which I definitely think should be ameliorated with more and more data. But I guess there's also a question where you also want to say, should the brightest minds all be investing their energy on just building larger capacity models with more GPUs and annotating more data, or should we really also be looking at more efficient algorithms?
So there's many people probably preparing some of those data sets. And to your point that, we're training to the data sets, not the task. Is there anything they can do to, make the challenge more effective or go beyond just data set preparation in some way? Any advice for people engaged in tasks like that?
Yeah, there's some interesting papers out. People have been trying to use adversarial neural networks to decide what are easy and what are difficult data points to classify. I mean, that seems like a nice and reasonable approach. Our work certainly indicates that if there's any way you can balance the linguistic artifacts over labels, that'll really make it challenging. This is a random idea. If you're doing a natural language inference data set, usually the premises all appear with one label once. If you could do the same with the hypotheses, then you'd eliminate, for example, the hypothesis-only baseline, which would, I think, would be a nice advance and make it a lot more challenging.
So what's next for your research? Is this a first step, or is this the, triumphant end of a line of inquiry?
In this particular area, there seem to be three things we can do. The first one you just mentioned, which is debiasing our data sets. I'm not working on that at the moment. The next one seems to be to try and find models that are more likely to learn the things we want them to learn, as opposed to latching onto these superficial statistics and data sets. And the third approach that I've read in the literature, something we are working on at the moment, is to start using out-of-distribution test sets. By out-of-distribution, we mean a different distribution to the training set in terms of how it's collected, maybe even a little bit of the details of what the task is, but still remains in the same domain. So it's the same problem. So we want to solve problems, not data sets, provide an out-of-distribution test set to see just how good you are, just how much you've learned the task. And so the hope is by doing so, you'll help guide the second problem, which is selecting models. The other thing that I'm working on in conjunction with the original authors of the argument reasoning comprehension task, is we're working on a new version of the data set. We don't have details of this right now, but keep your eyes open over the next year or so, and hopefully we can start to make some progress on this very challenging task.
Anyway, Tim, thanks again so much for coming on the show and sharing your work. Where can people follow you online?
I'm a little bit of a Luddite in not having much in the way of social media. My GitHub obviously will continue to have all the projects that we work on. Other than that, I would suggest Archive.
Yeah, I was going to say you implicitly have your archive page, which we'll link to as well.
Thank you very much.
Los Angeles, don't forget, October 26, 2019 at the LA Convention Center, the Southern California Conference on AI and Data Science. More information at ideassn.org.